Everyone knows steam engines run hot, boiling water, scalding metal, crews working in infernal heat even in the depths of winter. The entire principle depends on turning water into pressurized steam, releasing energy through controlled violence. Heat is the engine's lifeblood. So how did a steam locomotive freeze its own water supply while running at full power in the middle of a journey? It happened in Siberia. January 1936. The temperature had plunged to minus 58 degrees Fahrenheit, cold enough to crack steel, freeze diesel solid, turn human breath into ice crystals that tinkled as they fell. The Trans-Siberian Railway stretched across this frozen wasteland, a thin line of human ambition, through landscapes so hostile they defied comprehension. And on this particular morning, a Soviet Class E locomotive was about to demonstrate why extreme cold creates engineering challenges that no amount of heat can overcome. The paradox seems impossible. Inside the firebox, flames roared at temperatures exceeding 2,000 degrees. The boiler held superheated steam at 200 pounds per square inch, metal surfaces that would blister bare skin on contact. Yet the water in the tender, the car coupled directly behind the locomotive carrying fuel and water, was freezing solid. Not slowly, not gradually, but fast enough that ice chunks began clogging the feed pipes mid-journey. The crew realized something was wrong when the boiler pressure started dropping. Steam locomotives are straightforward machines in principle, but unforgiving in practice. Water enters the boiler, gets converted to steam, drives the pistons, escapes through the stack. The cycle demands constant replenishment. When the injector, the device that forces water from tender to boiler against steam pressure, started stuttering, the engineer knew they were in trouble. He could hear ice rattling in the pipes. Understanding how this happens requires confronting a brutal reality about extreme cold. Air at minus 58 degrees. Fahrenheit doesn't just chill objects, it actively pulls heat away with terrifying efficiency. The tender, essentially a large metal tank on wheels, has no heat source of its own. Every surface exposed to that Arctic air becomes a heat sink, conducting warmth outward into the void. The water inside might start the journey at a reasonable temperature, perhaps 50 or 60 degrees, heated by the depot steam pipes before departure. But once rolling through the Siberian night, that heat bleeds away. The mathematics are merciless. Water has high specific heat capacity, meaning it can absorb substantial energy before its temperature rises. That same property works in reverse. In ordinary winter conditions, say 10 or 20 degrees Fahrenheit, a tender full of water might cool slowly enough that a normal journey causes no problems. But at minus 58, the temperature differential is enormous. Nearly 90 degrees separates the water from the surrounding air. Heat doesn't just leak away, it pours out through every square inch of metal surface. Meanwhile, the locomotive itself is generating heat continuously. The firebox blazes. The boiler radiates warmth. Steam escapes from every valve and fitting, creating a perpetual cloud of vapor that freezes instantly into ice crystals. But none of that heat reaches the tender. The coupling between locomotive and tender is mechanical, not thermal. There's no heat transfer. The tender sits in isolation, a giant metal barrel of water being refrigerated by the Siberian atmosphere. The crew on that January morning tried the standard remedies. They opened the throttle wider, hoping to draw more water through the system and clear the ice. They tapped the pipes with wrenches, trying to break up blockages. They nursed the locomotive along, managing boiler pressure with the precision of surgeons. None of it mattered. The ice was winning. This wasn't the first time Soviet railways had faced this problem. The Trans-Siberian Railway, completed in stages between 1891 and 1916, had been battling Siberian winter for decades. Engineers had tried everything. They insulated tenders with wood cladding. They mixed the water with alcohol or glycol antifreeze, though this created other problems. Antifreeze contaminated the boiler, corroded fittings, and introduced chemicals into a system designed for pure water. Some depots tried adding salt, which lowered the freezing point but accelerated corrosion to catastrophic levels. The most successful solution was also the most brute force: keep the water moving. Depots installed steam heating coils inside tenders at major stations. Before departure, crews would circulate steam through these coils, heating the water to near boiling. The hope was that this thermal reservoir would last the journey. It rarely did on the coldest nights. Some railways tried a different approach entirely. They shortened the intervals between stations, ensuring locomotives never traveled more than an hour or two without access to heated water supplies. They built more frequent depot stops. They kept backup locomotives at strategic points, ready to swap out if a frozen tender immobilized a train. All of this required massive infrastructure investment and operational complexity. The Class E locomotive struggling through Siberia that January morning represented Soviet engineering's attempt to create a machine capable of handling these extremes. Built in the early 1930s, these locomotives featured reinforced frames, enhanced insulation around critical components, and boilers designed to maintain pressure even with intermittent water supply. They were tough machines built for tough conditions, but tough doesn't mean invincible. As the ice continued to form, the engineer faced a choice: stop completely and risk the entire locomotive freezing solid, or keep moving and hope they could coax enough water through to reach the next depot. He chose to keep moving. The alternative was worse. What saved them was ingenuity born of desperation. The fireman, the crew member responsible for maintaining the fire and managing water supply, realized that the very exhaust steam they were wasting could solve the problem. Every locomotive exhausts spent steam through the stack after it's done its work in the cylinders. That steam is still hot, still carrying energy. He rigged a temporary bypass, diverting exhaust steam into a pipe that snaked back along the locomotive's side and into the tender. It was crude, dangerous, and absolutely not in the operating manual. Exhaust steam isn't clean. It carries oil, soot, and contaminants. Introducing it directly into the tender water would pollute the supply. But polluted water was better than no water. The steam hissed into the tender, creating a roiling mass of hot vapor and ice chunks. Slowly, painfully, the ice began to yield. They limped into the next depot with the boiler pressure dangerously low, and the tender, a toxic mix of water, steam, and ice. But they made it. The locomotive survived. The crew survived. This incident, documented in Soviet railway archives, but largely forgotten outside specialist circles, illustrates a fundamental truth about engineering in extreme environments. Theoretical solutions often collapse when confronted with reality. On paper, a steam locomotive generates more than enough heat to keep its water supply liquid. In practice, that heat can't always reach where it's needed. The freezing tender problem exposed the limits of conventional steam technology in ways no amount of testing in moderate climates could reveal. Soviet engineers eventually developed purpose-built locomotives for Siberian service. These machines featured integrated tender heating systems, with steam coils permanently installed and fed directly from the boiler. The tender became part of the locomotive's thermal envelope rather than an isolated appendage. Water tanks received double-wall construction with insulation sandwiched between. Some designs even recirculated warm water continuously through a closed loop, ensuring nothing stayed still long enough to freeze. But even these improvements had limits. At temperatures below -65 degrees Fahrenheit, not uncommon in parts of Siberia, even the most advanced steam locomotives struggled. The diesel-electric locomotives that gradually replaced steam in the mid-20th century didn't solve the problem so much as shift it. Diesel fuel could be kept fluid with additives and heating elements. Cooling water still required antifreeze and constant monitoring. The cold remained an implacable enemy. The story of the freezing steam engine reveals something profound about the relationship between technology and environment. We build machines to conquer nature, to impose human will on inhospitable landscapes, but nature always retains the final word. A steam engine in Siberia must obey the laws of thermodynamics, just as surely as water must freeze at 32 degrees. The engineer's skill lies not in defying these laws, but in working within them, finding the narrow margins where human ingenuity can operate. Today, the Trans-Siberian Railway runs primarily on electric locomotives, drawing power from overhead lines. These machines don't freeze their own water because they carry no water. The problem solved itself through technological evolution, not through perfecting the steam engine. But the archives still hold those reports from January 1936, documenting the night when a crew fought ice and won, kept a locomotive running through sheer determination when the machinery itself wanted to quit. There's a deeper lesson here about forgotten struggles. History remembers the triumphs: the first transcontinental railway, the fastest locomotive, the most powerful engine. But it forgets the daily battles against mundane enemies: ice, mud, sand, wind, heat, cold. The crews who nursed machines through impossible conditions, who improvised solutions with wire and steam and prayer, who kept the trains moving when everything conspired to stop them. These stories disappear not because they lack drama, but because they lack the narrative simplicity we demand from history. The steam engine that froze its own water wasn't a failure. It was a machine operating at the absolute edge of its environmental tolerance, revealing truths about physics and engineering that no laboratory test could demonstrate. The crew that saved it weren't heroes in the conventional sense. They were professionals doing impossible work in impossible conditions, using knowledge earned through experience that no textbook could teach. That's the real story of technology in extreme environments, not the glossy promotional photographs or the grand pronouncements of progress, but the frost forming on metal, the desperate improvisation at 3 a.m, the choice between bad options and worse ones, the knowledge that sometimes keeping a machine running is less about engineering excellence and more about refusing to accept the obvious answer, that some things simply can't be done, and yet they were done. The trains ran, the water froze and thawed and froze again. The Siberian winter won every night and lost every morning. The locomotives kept rolling, imperfect machines operated by imperfect people, fighting a war of attrition against the coldest places on Earth. The next time you hear someone say, "Steam engines run hot," remember, not always hot enough.